Hello, today we'll be talking about oxygen, carbon, and nitrogen nucleophiles and their reactions with aldehydes and ketones. So first to start out, we'll draw a good example of a ketone, which is essentially just this. I'll call this ketone. And here, this is an aldehyde. So the main difference between aldehydes and ketones is that aldehydes, instead of having two R groups, you have a hydrogen instead. So when we're doing it, when we take an example such as, we'll say here, we have to determine which is a nucleophile and the electrophile. So by doing this, we have to understand essentially which is going to be more, which has will donate more protons and which will take more take protons or electrons and take electrons. We can do this by making a resonance structure where we can go here, creating this. By having this, we can safely say that oxygen is the electrophile, as it has more electrons, and the nucleophile is one of these R groups. So we can actually take an example where we use an aldehyde and oxygen to determine make a reaction with that. So one example, this we consider an acid reaction, where we have an aldehyde, R and H. We'll react it with hydronium ion, which is an OH3. So we first off will take these electrons and attack hydrogen. This will be considered a proton transfer. From there we have this R and H. And we can use now water. Oops. As a way for reacting, and these electrons can push on this double bond, breaking it, causing this double bond to break and put the electrons on the oxygen. I can write this a little bit better. So now, because we have a single bond between carbon and oxygen, we have this reaction, or this product. The water is right here, and we have an R and an H. We can further use water again to deprotonate one of the water in the compound. We can take this out and do another proton transfer to now get OH, and then an R and an H. And that's how it is. So when we're looking at nucleophiles and basicity, in general, when you look at nucleophiles on the periodic table, let's say CNOF, then you have Cl, bromine, and iodine. Nucleophiles increase going down periodic table. However, basicity increases going up. At the same time, nucleophiles and basicity both increase going across the periodic table to the left. So when we're taking an example of different aldehydes, it's important to note which nucleophiles to use, what compounds are good nucleophiles for the reaction. A good example of this is taking another aldehyde, for example, and reacting it with, we'll do a triple bond of CN. So we'll go this. So we know that carbon's a pretty good nucleophile, and because of that, we can have it attack here, this carbon, pushing these electrons onto oxygen. And of course, we'll actually put this proton there to show some transfer. And from there, we can now have carbon, triple bond with cyanide, nitrogen, along with electrophilic oxygen, and R and our H group here. Because this is still wants to electrophilic, it's going to want to take a proton. We can use the hydrogen atom here, and this oxygen can pick up the hydrogen atom, giving a final product CN, R, H, and OH here. However, when you look at different reactions, one of the more important things is to understand what type of carbon or aldehyde you're dealing with. So in this example, we obviously had a 2', but now let's shift gears a little bit and take a look at a 3' ketone. So a ketone, like I said, is similar to an aldehyde, except that there's 2 R groups instead of having a hydrogen group. So we'll say this is R1, this would be R3, and we'll react it with alkyne, we'll call this R2. So, again, because of our product, we can again push this way, causing this electron to go on an oxygen, But we can get a final product. And then again, we have this. But essentially, when you do the reaction, we can get a final product of R3, R2, and of course, R1, and then this of R2. So it's important to know where your the position of your carbons are for aldehydes and ketones. So now we have to understand how to do different types of how do I say this? Retrosynthesis. And by doing that, there's a couple reactions that we should know. So in general, we'll take an example such as, let me think here. Here, we'll go with a Euclid in a reaction. So we'll use this. It's also called Whitting reaction. And just be a simple one for now. Essentially, we'll use PH3P on a methyl bromide group, Br. So when we're dealing with this, we'll first put this onto carbon, taking off the bromide. From there, we'll then have PH3P plus bonded to a CH2H. We can use, and this will be through an SN2 reaction, obviously. From there, we want to form the yelid by removing of a proton using a strong base. A strong base could be, we could use Bu lithium, for example. And when we do that, we can deprotonate this hydrogen and put this bond onto carbon. With that said, we'll now have PH3P CH2 minus, because we have now another set of electrons, and it's still plus here. However, because of this, we can actually form a double bond, a resonance structure, by putting these electrons onto the bond, creating PH3P CH2. And that is an example of a carbonyl group reaction, Witting reaction. And yeah, I think that's it. Trying to think of anything else that we can go over. One more thing. I think this is incredibly important. When we're looking at hemiacetal formations in ketones, it's important to note that trying to find these things. So hemiacetal, depending on how you say it. We'll use a ketone, for example, and when we use ROH to 1 equivalent, that can produce essentially an OROH product. So when we're looking at hemiacetals from ketones, one important thing is to know that an oxygen and hydroxide coming at the same carbon creates an hemiacetal. So essentially, when we're doing the mechanism for this ketone will bind to one hydrogen, causing this to go. From there, we'll now have this, and we can have an OH, and then have an R group here, and this group can attack the carbon, moving this bond on, coming electrons on oxygen, creating OH, water, or hydrogen and R group. And this. From there, you can use an acid to attack this hydrogen, bumping it off the oxygen, because it's a plus, leaving us with final product of OR. And of course, again, when I said it before, but the hemiacetal, when you have an oxygen and hydroxyl group centered at the same carbon, we consider this an hemiacetal. Thank you.